There we go. Where's my cheat sheet? Right. Tim, are you ready? Can I say a few words?
Yeah,
okay.
I'm good to go.
Okay. Welcome back, everybody. Today we're going to hear from Tim Beldon. Tim's a member of the ICOMOS-UK Wood Committee. He's a PhD postgraduate researcher at the University of Surrey. And currently he's undertaking research into the reduction of the load-bearing capacity of metal fixings in timber due to pyrolysis, which I'm sure, as you'll all know, is the decomposition of materials brought about by high temperatures. This work is applicable to both historic timber frames and new engineered timber buildings. Tim's research is also applying computer vision and machine learning techniques to 3D map, monitor, and measure movement in structural timbers. Tim gained his MSc in building conservation from York and is also a trained millwright specializing in the conservation of repairs to wind and water mills. Between 2012 and 15, he was senior partner at the Norfolk Millwright Alliance. And for the past 10 years, he has also been running his own business, offering technical advice on water mills and windmills, and as a training and management consultant, including 2 years as manager of TRADA's University Engagement Program between 2015 and 2017, which is when I met him. So that's enough. Tim, now it's over to you.
Okay, thank you, Doug. Welcome, everybody. So I thought I'd talk about what researchers actually do. And as I was explaining before we started, most of that is drinking coffee and talking. So what I thought we'd have a look at, if I can get the computer to work. I've got a couple of themes for this evening. So most of this will be talking about imaging processes and ways that you might be able to use that in your own lines of work. So hopefully there's at least one thing in here that will be applicable to everybody. We'll have a quick look at 3D mapping and how you might be able to achieve that. A quick talk about how we can apply some of these techniques to building safety, and a little about where everything seems to be going for the future. I was talking to Doug before we started about how research kind of evolves. I first started this by looking at resins and resin bonds in timber, and very quickly started to realize there's quite a lot of research out there. So I then started to look at the application of fire to metal fixings in timber connections. And that very quickly, because there's very little machinery or processes that you can use to examine that sort of thing, very quickly ended up designing my own equipment. And that led me into these computer vision applications of how we can monitor, measure, and kind of map things in our world of timber. So over the course of the last 3 years, which is pretty much what I've been doing this research for, my focus has always been how can I design and develop things which would make wood research affordable, especially for kind of small and medium enterprises out in the real world, and students as well, because a lot of the machines in the university are tens of thousands of pounds, and some of them are millions of pounds, and most businesses aren't going to have the money to apply that kind of machinery to their research. So lots of the things that I've built and the research I'm doing is in the hundreds of pounds mark rather than the tens of thousands of pounds mark. And the more I've got into it, the more I've realized we can apply a lot of these techniques to many applications in the work which you're all doing. So don't turn off just yet. I know I'm going to talk computers, but don't turn off just yet. So when we think about computer vision, probably these are the sorts of things that you're imagining, either number plate recognition or some clever little program that will identify various things in a picture. And whilst that's a useful technique, that's not the sorts of applications that we can use it for timber. So I'm going to show you one of the first uses I put the computer vision to. And on the left here, we have a piece of wood. Now in this piece of wood is a metal fixing, of which I'm going to heat in a second. The second, what is blank at the moment, is actually this first image with the flames. As you see the flames start to come down here, it'll show you which piece of wood is actually being burnt. And then this last image would allow us to measure how quickly that flame is moving. So I'll play the video for you. So at first you see nothing, and then from the top on the left hand side you can start to see the burn marks start to creep down the piece of wood. Now this middle image here is actually the wood itself, which is currently being burnt on this image. So it would lead us perhaps to see, there are certain features in this piece of wood which allow it to burn more quickly than other sections. Now this was a relatively easy piece of programming. It merely adds and subtracts images from each other. So the way you could apply this, if you were Doug, for instance, doing a quinquennial, you could have a series of images of the building, and then you could subtract one image from the next, from the next, from the next, and that would allow you to detect any movement in the building within those images. So that would be like a movement over time effect. And really that's just a matter of subtracting one image from another and seeing what's left. If you were doing a long-term archaeology sort of dig, you could apply that to layers of your dig and see what materials are appearing over time. So this is really just adding and subtracting images from each other. So the latest piece of work, although it's got many features of the older pieces of work, is to take a small desktop CNC router. So we've got a little table here which moves backwards and forwards. We've got a little head at the top here which slides left and right, and then the actual part moves up and down as well. And what you can see on the right hand side, I've replaced the cutting head with a small microscope and plugged it in, and so you can see an image of the wood with a small piece of notebook. It's actually a small 5mm square piece of the notebook under it. So what we can do is, by taking this video feed, plug that into the computer and tell it we're only interested in this particular color. So again, if you had a camera on site and you were doing archaeology and you wanted to pick up a particular color of item in the ground, which was hard to see, you could alert the camera to give you an audio signal as soon as it detected that particular color within the image. And so here's the first image. On the left hand side there's a short piece of computer code, and this is the output that the computer says, I'm not interested in any of the black area, there's the square, and hey presto, there it is in white. And you might be saying, well, that's great, but you know, not very useful perhaps, you might think. So what we can do is apply that to the machine, and we can say, here's my piece of wood on that sliding table, find the top edge for me. And so as it moves the camera around, suddenly the top edge appears, it detects that it's reached the top edge, and then it goes to hunt for the bottom edge. So we're really just using those color values and detection of those color values to start to move the machinery around. So again, it could be that you're taking off paint layers maybe, and you want an alert when a particular background color appears. Again, you could apply this technique to it. So it's not just detecting that edge. At the same time, the microscope is taking a series of pictures. As you can see from these images, that it sequentially, every time it moves the stage, it takes a microscope picture for me. And then eventually it adds all of those pictures together. So if I was scanning maybe a ceiling or something, I could make the machine any size I like. The microscope can then travel backwards and forwards over whatever it is that I'm scanning in, and suddenly now I've got a digital record of the artifact that I want to scan, similar to a kind of a 3D scanner, but we can record it at a microscope level as well. Now, anybody that's ever put a piece of wood under a microscope knows how time consuming that is to look at section after section after section. This is now at the stage where you can put your sample on the bed, press the computer, go and make your cup of coffee, go and do something else, and then come back half an hour later and it's scanned the entire sample. Now, at the moment, I'm scanning samples up to 300 millimeters by 180 millimeters. As I say, the machine could be made much, much bigger without any problems whatsoever. So you could scan whole kind of table-sized artifacts or an entire room if you really wanted to, using this technique. You could then also take these computer vision or these pictures and do photogrammetry or something else on them that you then wanted to use the images for. So the next step is if you were looking at wood under the microscope, rather than try and measure certain features, just get the computer to do that for you. So here we have the original microscope slide. We've got a little scale bar, a little red scale bar on that top left image. In the bottom left, you can see I've asked the computer just to find the
Well, Houston, we have a malfunction.
Tim, you've frozen. Check your connection, Tim.
Where's he gone?
This is why we have to pre-record presentations for a conference that I'm helping to organize. It's tough.
Is that you, Evan?
Yeah, that was me talking.
Oh, hi. Hi. There, everybody's on my screen now. Great. Cool. Yeah, it looks like there's Peter, there's Maria. Hey, great.
Evan, do you want to give a quick plug for APG?
Yeah, there's for those of you, I guess it's probably more popular in North America, but the conference was supposed to be in Edmonton this year. It's primarily a virtual conference, but we're still trying to keep with the theme of Edmonton, and there's definitely going to be a lot of local content. And there is going to be a vernacular wood and earth architecture workshop, which Andrew's helping out with, as well as Susanna here. Yeah.
Oh, it's nice to see you again.
Yes, good to see you.
Yeah, we have a beautiful summertime Mexico with a lot of rain.
How are things in Guadalajara?
Back. Are you back, Tim?
The things are good.
Oh, okay.
There he is. Okay, Tim.
Tim is back. You got to be unmuted.
Still muted, Tim.
Still
There we
muted.
go. There we go.
Okay.
Right. Let's get the screen back. Not that one.
Did the dog knock the plug out?
There we go. I think it's our internet connection. They've been doing works I think we're finally going to get fibre in our village eventually, but it's been a long time coming. Right.
Okay.
We were kind of here somewhere.
Not only in Argentina.
Sorry. Here we go. Can you? Oh.
Yeah. No, crack on.
It's
Yeah.
not only in Argentina. It's Argentina is difficult.
So, as I was saying, what we can do is get the computer then to measure the size of.
Got to share the screen, Tim.
Oh, has it not shared?
Oh, yeah.
Shared screen. Hold on. Share.
There you go.
Ah, okay. We're there. Sorry about that.
Perfect. Good.
Okay, so we can get the computer to measure the size of things in any of the images we chuck into it. So it could be measuring the number of windows in a row of houses, if you were interested, or the size of the windows in a picture you had of historic houses. You could be using it to measure the size of components of a frame. So we could apply this technique to literally measure anything. As long as we've got a scale bar in the image, and we tell the computer to look for that particular color of scale bar, it can then size everything else within the image for us. So to take that technique another step further forwards, and as I say, my research is looking at tedious slicing of pieces of wood and then seeing how that burn process expands through the piece of wood. Now, the only way you can do that is to burn the piece of wood first and then slice it, which is really time consuming. You've got to take a slice, take a picture, take a slice, take a picture. And this was where the work with the router was going. Whoops. Let's jumped. So the process then, if you want to take these slices and turn that into a computer model so that you can then do other analysis on it, is to have your photograph. So the image on the left represents our photograph. We select the color values that we want to track. In my case, it's burnt pieces of wood. And then we feed a number, any number, in this case 3 images, into the computer, and we say produce a little voxel, a little cube, when you find any pixel in that image of the color value that you tell it. So we could be looking for anything in either a series of timed images, so we could see the growth of maybe I don't know, ivy across the face of a building, and we could turn that into a 3D image, which we can look at later. Or in my case, as I say, I'm looking at the extent of burn within timber. So I'm looking for burnt pieces of timber within the pictures that I feed into it. So why do that? Well, that allows me to then build up a 3D image. So here we have the kind of, on the left, the top view, on the right, the perspective view, and I can see the extent of the various degrees of burn throughout the piece of wood. So we start with what is the nail hole in the middle, or the screw hole in the middle, and I can work out layer by layer what's the speed of that burn throughout the wood. Now, the advantage is, as you can see in this image on the left, it allows you to detect the extent of burn all the way down that kind of section of screw and see whether it's uneven or not. So you could take your computer model and do almost anything with it. Another example, which is perhaps more useful, is you can then share that image once it's a computer model with your colleagues, and using a bit of augmented reality, we can project it onto a piece of paper. So that was a picture of some wood cells, and by simply having a piece of paper with an image that the phone in this case can detect, I can project an imaginary section of wood onto that piece of paper. Now, the reason this is useful for anybody that's got students and a limited number of microscopes is you can take a picture of the slide and then you can share it with all of your students, and all you need is one piece of printed paper each, which is far more achievable than 50 microscopes. So again, this is applications which is relatively inexpensive. Once you've got that computer model, you can manipulate it in a huge number of ways. Now, it could be you're showing your newly designed frame to your customer and do exactly the same thing. All you need is the phone and a small printed image. So by sectioning your pictures up and turning it into a 3D CAD model, you can achieve quite a lot with it. So moving on to building safety, what could you do? Well, you could take a series of images. This is another technique which basically just detects edges. So the picture on the right is a beam bending rig at the university. The picture on the left is, the picture on the right is that same picture, but with edge detection applied to it. Now, we could do that with a wall that we were concerned about, set up a cheap camera, leave it running, taking a series of pictures, and when the edges start to move, it could send us an email, it could sound an audible alarm. We could do anything from the fact we can detect changes between each picture. We could also connect the image. It doesn't have to just be like a phone camera image. It could be an infrared image, or because we're looking at computer numbers essentially, we can also use audio signals as well. So we can even detect changes in those, pretty much using the same software. So where are we going with all of this? Well, ultimately the next stage, now I've managed to get the computer to talk to most of the small motors quite happily. We can, now I've pinched this off YouTube, so you can go and have a look at it. But it is a little laser scanner, which has got a small computer motor attached to the bottom. It scans backwards and forwards and measures the distance. So for something in the order of a few £100, you can build yourself a little LiDAR, a laser distance scanner, to map the room for you. Rather than at the moment, those laser scanners are in the order of £20,000 plus, or £1,000 or more a day if you want to get somebody in to use them for you. Now, it can now be built for a few £100, which you've then got to use forever. Set it up in the room, hook it to a small tablet, and that'll actuate the motors, and it'll sit there and map the room for you. So that's where the tail end of my research is about to go. I was hoping to show you it tonight, but haven't quite got it up and running yet. But that's the trials and tribulations of research, I'm afraid. So they are some of the applications that you could put some of these techniques to. I hope there's at least something in there for most people. Happy to answer any questions. Thanks very much.
Right. Thank you, Tim.